lab report for the microscopic view of DC and RC circuits. The purpose of the lab is to predict the behavior of circuits containing resistors in series and in parallel, and examine the behavior of ohmic resistors and capacitors. The key concepts needed are the node rule, which states that all the currents of each individual component of the circuit add up to the total current, and energy conservation, that the sum of the potential differences across each component of the circuit adds to zero. We also need Ohm's law, which is a formula relating current, resistance, and potential difference, and it can be written as V equals IR. For part 1, we're given a circuit, and we're asked to predict what each ammeter would read. So the two ammeters would read the same value because of the node rule, and we can use Ohm's law to calculate what that value would be. When we calculate that value, we get 0.02 amps. When we construct the circuit in the simulation, we get that the two ammeters both read 0.02 amps, which matches our prediction. If we were to reverse the connections on one of the ammeters, we would get negative 0.02 amps, which is because the current is flowing in the opposite direction through the ammeter. So now we replace one of the ammeters with a voltmeter, and we calculate the voltage reading to be 3 volts and the current to be 0. And this is because the voltmeter acts like a resistor with infinite resistance, which effectively makes the circuit open, so there's no current flowing through the ammeter. Now we want to calculate the potential differences across each of these points in the voltmeter. We find that the total potential difference is equal to 0, which supports energy conservation. This is a graph showing the potential difference across each individual part of the resistor, and we see that it eventually goes to 0. When you attach the voltmeter, you alter the circuit. Why doesn't the ammeter reading change? The voltmeter measures the potential difference, and it does not alter the current. We are also asked what would happen if we replaced the voltmeter with the ammeter in parallel with the 100 ohm resistor. What would happen to the current through the other ammeter? The current increases to 0.06 amps because less current crosses the resistor. Now we're asked to calculate the resistance of the 47 ohm resistor and the 100 ohm resistor, as well as the wire and ammeter. We get the values to be slightly different for the 47 and 100 ohm resistor, and this could be due to the lack of precision in the ammeter. We find that the resistance of the wire and ammeter are both 0, which supports our assumptions. For part 2, we're now charging and discharging a capacitor. So when we first connect the circuit, the light bulb is bright, and then it eventually dims and goes out as time passes because the charge is being held in the capacitor. If we remove the battery and connect the circuit again, the light bulb is bright because the capacitor has the charge, and then it slowly dims as the capacitor discharges. What happens to this current in the circuit? So the current in the circuit was decreasing gradually until it reaches 0, and then when we discharge, the current starts at a high value and then decreases to 0 again. So we measured the time for the capacitor to charge using a 10 ohm light bulb and a 20 ohm light bulb, and we also measured the time for a 10 ohm light bulb and 20 ohm light bulb when we are discharging the capacitor. So then we are going to take measurements after we charge the capacitor and then discharge the capacitor using a stopwatch and timing it for 20 seconds and taking observations of the voltmeter about every 1 second. So we get this data table, and then in the rightmost column we calculate the natural log of the delta V over the initial potential difference, and when we plot this we get a negative slope linear function. To calculate RC, which is the time constant, we use the slope of the graph, which is negative 1 over RC, and we use 2 points to calculate the slope, and then when we solve this equation, we get RC is 5.56 seconds. For the reflection questions, if we were doing this lab in real life and used an actual ammeter instead of an ideal ammeter, what's different about the real ammeter? So a real ammeter would have resistance, so the readings would be less accurate. If we were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit, so if the circuit was set up perfectly, the capacitor would charge instantaneously, but since all components have resistance, it would take some amount of time.